So the first talk is by Shivam about quantitative correlation inequalities via semi-group interpolation.
Yeah, thanks, Avishai, and thank you all for sticking around for the last session of today. So this is joint work with Anindya and Rocco, and it's about correlation inequalities. So let me start off by telling you what a correlation inequality is. You've got some probability space, and you're interested in some family of functions on this probability space. And a correlation inequality simply tells you that any two functions belonging to this family are non-negatively correlated. And these are very fundamental tools in combinatorics and statistical physics. If you grab your copy of Fallon and Spencer, you'll find a full chapter devoted to these sorts of statements. To make things a little more concrete, let's look at perhaps the simplest correlation inequality, the Harris-Gleitman inequality, which says that any two monotone Boolean functions on the n-dimensional hypercube are non-negatively correlated. So just to remind everyone, the n-dimensional hypercube is just the collection of 0, 1 strings of length n. And a function is said to be monotone if flipping a bit from 0 to 1 cannot cause the value of the function to decrease. Another correlation inequality is Royne's inequality. This was proved in 2014, and it concerns symmetric convex sets of a Gaussian space. By Gaussian space, I just mean Rn endowed with the standard Gaussian distribution, and a set is symmetric if it's symmetric about the origin. Or in other words, if a point x is in the set, the point obtained by reflecting x through the origin, or in other words, flipping the sign of each of x's coordinates, is also in the set. And what Royne showed is that if you've got two symmetric convex sets, then the indicator functions of these two sets are non-negatively correlated with respect to the standard Gaussian distribution. Another way of stating Royne's result is as follows. It simply says that the Gaussian measure of the intersection of two symmetric convex sets is at least the product of the Gaussian measures of the sets themselves. And there's many other correlation inequalities for interesting classes of functions on different domains. But since we only have 8 minutes, let's focus on the two examples we just saw. So one thing to note about both these statements is that they're qualitative statements. All they say is that this correlation between these two functions is non-negative. And it's natural to hope for a better lower bound on this correlation, perhaps in terms of some property of the functions we're looking at. So with this in mind, let's actually revisit the Harris-Gleitman inequality. And when you're thinking about Boolean functions, perhaps the first property that comes to mind is the notion of influence. So this is a very standard notion. Given a Boolean function on the n-dimensional hypercube, you can define the influence of any of its n coordinates, say the ith coordinate, as the probability that when you choose a point uniformly at random from the Boolean hypercube, the value of f at that point differs from the value of f at the point obtained by flipping the ith bit of the original point. And this influence captures, in some sense, how much the function depends on the ith coordinate. And there's been a very long line of very interesting work built around this notion of influence. And we saw some new proofs of the results I mentioned just in yesterday's analytic method session. So returning to correlation inequalities, in 1996, Talleyrand proved the following robust version of the Harris-Gleitman inequality. He showed that if you've got two monotone Boolean functions, you can lower bound the correlation in terms of this function psi of the sum of the products of the influences of the two functions. And this sum of the products of these influences, it captures in some sense how much the two functions depend simultaneously on the same set of coordinates. And this quantity actually arises very naturally in the proof of the Harris-Gleitman inequality itself. So it's not very surprising. And this function psi of x is just defined to be x over log of e over x. So to summarize the situation so far, we've got these two nice qualitative statements, the Harris-Gleitman inequality and the Gaussian correlation inequality or Royne's inequality. And Talleyrand comes along and robustifies the expression on the left. And you've got this really interesting quantitative correlation inequality now for monotone Boolean functions. And it's natural to hope for a similar statement for symmetric convex sets of a Gaussian space, or if not a similar statement, some quantitative version of Royne's result. And that's precisely what we obtain in this work. We show that given two symmetric convex sets, you can lower bound the correlation between them in terms of this function phi of the sum of the products of these influences. And this function phi differs from Talleyrand's psi function in that it's got an additional logarithmic factor in the denominator. But I also haven't told you what this notion of influence for a symmetric convex set is. So let me briefly define that. It might be a little technical. So if you've got a symmetric convex set, the influence in the ith direction of that set is the negated degree 2 Hermite coefficient So for those who are familiar with Boolean function analysis, the Hermite basis is sort of similar to the parity basis for functions on the hypercube, but it's a basis for functions of a Gaussian space. And these coefficients are sort of analogous to the degree 1 Fourier coefficients of a Boolean function. And if you're not familiar with it, just think of it as this expectation of the indicator function with this polynomial 1 minus xi squared scaled by √2. And this notion of influence really does behave like a notion of influence. In particular, it's non-negative with equality if and only if the symmetric convex set K is independent of the ith coordinate. In other words, it's sort of a cylinder along the ith direction. And many other interesting analogies with seminal results from Boolean function analysis seem to hold for this new notion of influence, and we've been exploring this notion further. So returning to the quantitative correlation inequality that we prove, suppose K and L are two symmetric sets. We know that the value of the expectation of K times L is greater than the value of the expectation of K times the expectation of L because of Royne's inequality. And what we do is we actually interpolate between these two quantities. And there's a natural way of doing this by starting with the quantity on top and adding noise to one of the two functions. And you eventually add enough noise that this noisy version of, say, K becomes independent of L. And this expectation splits into the expectation of K times the expectation of L. So let's introduce this noise parameter rho. When rho is small, you should think of the noise rate being very high. And when rho is large, close to 1, we're adding very little noise. And suppose we interpolate using this noisy process that I described. More formally, it's given by this Ornstein-Uhlenbeck noise operator. And we get this curve that looks like this. Now, the Hermite basis lets us write this curve as a power series in rho. And our main technical lemma is this complex analytic tool, which essentially tells you that the value of this power series at some point along this interpolation is large. But this isn't enough to conclude that the correlation is large because the value of the curve at the right endpoint might be much lower than the supremum of this curve. And so let's actually ask Royan what he thinks of the situation. So here's Royan. He's looking at this curve I put up, and he's clearly not very happy because what he actually shows is that this interpolation has to be monotone. Or in other words, the curve is going to look something like this. And this monotonicity lets us actually conclude that the correlation is going to be large. And so let me put this sketch of a proof a little more abstractly. You've got some probability space and some family of functions you're interested in. And you can interpolate between the two terms in this correlation quantity by means of some appropriately defined Markov semigroup. Now, once you've got this interpolation, you can express it as a power series using the eigenfunctions of this Markov semigroup. And our complex analytic lemma tells you that the value of this power series is large somewhere along this interpolation. And finally, this monotonicity of this interpolation lets us conclude that the correlation is large. And this monotonicity is often available in the form of off-the-shelf results. So people prove this monotonicity to prove qualitative statements. And so this lets us obtain quantitative correlation inequalities in a bunch of different interesting domains by choosing an appropriate Markov semigroup. And there doesn't seem to be a canonical choice of Markov semigroup to put on some of these domains. For example, on the solid cube, for each different choice of Markov semigroup, we get a seemingly different quantitative correlation inequality. So here's a quick summary of everything I just described. The longer video is up on YouTube, and the full version of the paper is on arXiv. And thanks for watching.
Thank you for the great talk and wonderful result. Okay, so maybe
Stop sharing.
should stop sharing screen, and we should move to the next speaker. And it's good if you have a quick question you can ask now. Okay, so maybe we'll leave the questions for later. And next we have Sasha Golovnev talking about circuit depth reductions.
Yeah, hi everyone. Thank you for watching. Yeah, my name is Sasha Golovnev, and this is a joint work with Sasha Kulikov and Ryan Williams. In this work, we suggest a new way for proving circuit lower bounds. So we do not prove any new circuit lower bound, but in particular, we show how improvements on the known constructions of various pseudo-random objects would lead via our framework to new circuit lower bounds. Okay, so first let me remind you the computational model. We're going to be talking about this is a model of Boolean circuits. Here we want to compute a function from n bits to 1 bit, and we're computed it by this directed acyclic graph that is called a circuit. And this graph has n inputs, and every gate computes a Boolean function of 2 Boolean inputs. Okay, and we do not pose any restrictions on the out degree on fan out of gates. All right, so a simple counts and argument show, and the size of the circuit is just the number of gates in it. And the simple counts and argument shows that most of the functions require circuits of exponential size. But the challenge is to find an explicit function, say function from the class NP, that is hard for circuits, that cannot be computed by a small circuit. This is the problem of circuit lower bounds. So even if we prove a super polynomial, just super polynomial lower bound for a function from NP, we separate P from NP. So even though we know that most of the functions have exponential complexity, we actually need to only prove super polynomial lower bound, and the best what we can do is roughly 3n. Even if we're trying to prove circuit lower bounds for functions from a much larger complexity class, the class of exponential time algorithms with an NP oracle. And this NP oracle in turn can even take inputs of exponential size. So even for huge classes, the best circuit lower bound we can prove is roughly 3n. And so when we can't prove a lower bound for a computational model, we usually consider weaker models. So here a natural special case is the class of circuits of bounded depth. So say if the depth of a circuit is just 2, then such a circuit can only compute CNFs or DNFs. And this essentially is the only circuit models that we understand well. For example, we know that even the parity function, very explicit function, would require such circuits of exponential size. But even if the depth is 3, 4, or any other constant, we still know how to prove exponential circuit lower bound. Now, if the depth is logarithmic, say 1.9 log n, and every gate again computes a function of two inputs, then we know functions that are hard in this model that cannot be computed by circuits of depth 1.9 log n. But already for depth 2 log n, we know nothing. We know nothing non-trivial. Again, the best circuit lower bound is roughly 3n. So the main problem on the frontier is proving anything better, say superlinear lower bound, at least for log depth circuits. All right, so and why is this problem so hard? Because essentially the only technique that we know for proving circuit lower bounds in this models of high depth is a technique called gate elimination. And it's bad for several reasons. This gate elimination is always ugly case analysis. We don't want to do this. And also, probably, it cannot lead to interesting circuit lower bounds. Gate elimination cannot give us anything better than, say, 5n, which is clearly not that exciting. Okay, so we desperately need new techniques for proving circuit lower bounds, something different from gate elimination. So in this work, we suggest one such technique. It doesn't lead to new circuit lower bounds immediately, but hopefully maybe sometime later. But first, I want to say that in the 70s, Valiant already gave an interesting non-gate elimination technique for proving circuit lower bounds, but for special case of circuits, for circuits of logarithmic depth. Namely, in the 70s, Valiant showed that every circuit of linear size n logarithmic depth can be computed by a non-trivial depth-free circuit, by a depth-free circuit of sub-exponential size. So if you prove a strong exponential lower bound for depth-free circuits, it translates to superlinear lower bound even for log depth circuits. All right, so Valiant reduces the depth of a circuit from order of log n to 3, and his proof uses a circuit as a graph. So it never looks at what is computed in this, at every node of a circuit, but it views it as a graph. And it's known that such graph theoretic techniques cannot work for circuits of super logarithmic depth. So the first result of this work will show that we also do depth reduction for circuits of unbounded depth, but unfortunately only a small size, of size roughly 4n. Okay, so the first result of this work is depth reduction for even unbounded depth circuits, but only of size roughly 4n. Every unbounded depth circuits S can be computed by the following depth circuit, and this is interesting when the original size is less than 3.9n. So again, a random function cannot be computed by such a depth circuit, and we show that any improvements on the known pseudo-random objects, on the known constructions of pseudo-random objects, would also lead to the circuit lower bound for unbounded depth circuits. Also, we prove a similar result for unbounded depth linear circuits and matrix rigidity. We show a new connection between these two terms. Finally, we apply our framework for two De Morgan formulas. So a formula is a circuit where out degree of every gate is exactly 1. You cannot reuse computation. And De Morgan formula means that you cannot use XOR gates, only ANDs, ORs, and NOTs. A long line of very beautiful works leads to essentially cubic lower bound on De Morgan formulas. And in this work, using this depth reduction framework, we give a way of studying De Morgan formulas of size n to the 4th. All right, that's it. Thank you for your attention. I'll be happy to take any questions either now or at the end of the session.
Okay, thank you very much, Sasha, for a great talk. I think we have time for like 1 or 2 questions while Ben sets up.
What is the plausible assumption in your last theorem?
Yeah, unfortunately, I didn't have time to cover it. In short, it says the following, that a De Morgan formula of size S has a probabilistic polynomial of degree square root of S. So we know that it has approximate polynomial over the reals of degree square root of S. We would like to say that it also has a probabilistic polynomial, say, over 2 of same degree.
Thank you.
Thank you, Sasha. Okay, so maybe let's continue to the next talk by Ben Rossman, Shrinkage of Decision Lists and DNFs.
All right, so I'll start by defining the models that we consider. So DNF formulas we're all familiar with. So we have a disjunction of conjunctive clauses. So each clause or term is just a conjunction of literals. So a decision list of size M is a sequence of M clauses and M output values, where the disjunction of C1 to CM is a DNF tautology. So it's true on all inputs. So, and without loss of generality, the final clause could just be the empty clause, which is always true. And here we let, the output values can be anything, not necessarily Boolean valued. And a decision list computes a function by simply outputting the ith output value where I is the index of the first satisfied clause. Okay, so I'll also be discussing decision trees and De Morgan formulas. Yeah, we're all familiar with the definitions here. Okay, so for function f on the hypercube, we can define its decision tree size and its decision list size. And in the case of Boolean functions, we also have DNF formula size as measured by number of clauses, and De Morgan formula leaf size denoted L of f. Okay, so decision lists are a generalization. They're more powerful model than decision trees. So, for any function, its decision list size is at most its decision tree size. For Boolean functions, we see that decision lists are sort of more powerful than both DNFs and CNFs, which are more powerful than decision trees. And we also have width or depth versions of all of these size measures. And these satisfy the inequalities that you see below. Okay, so the P random restriction, we're all familiar with also. So this is a random assignment, partial assignment of the variables, where a variable is left free with probability P, otherwise set to 0 or 1 with equal probability. And right, so for an n variable function, we get this randomly restricted function. So it's well known that the p random restriction reduces the complexity of Boolean functions as measured by these simple complexity measures. Oh, I forgot to start my timer. So Avishai, just let me know when I have a minute or two left. Okay, so right, so the classic result on the effect of RP on these simple complexity measures, the shrinkage of De Morgan formulas. So so it's known that the expected formula size of a Boolean function under RP shrinks like p squared, okay, by a factor like p squared. And yeah, we saw a very nice generalization of this result earlier in the conference to a more general class of random restrictions. So another result showing the power of RP on this time on DNF or CNF formulas is the switching lemma, right? So this shows that a small width DNF formula converts to a small width CNF formula with high probability. Okay, so so here on the slide I state the results in this paper. So we look at shrinkage of decision lists and decision trees, and the results are as follows. So for decision trees, you can show that the expected decision tree size shrinks much faster than any constant depending on p, but rather it shrinks like the decision tree size to the power log 2 of 1 plus p. Calling this a folklore result, the proof is a very simple induction. And I mean, I don't know of a reference for this, but anyway, so proof's included in the paper. And then our main result shows that decision lists, so this more powerful model, the size of decision lists shrinks at a similar rate to decision trees. So it shrinks like decision list size of the original function to the power log base 2 over 1 minus p of 1 plus p over 1 minus p. Okay, and the same bound applies to DNF formula size plus 1 or CNF formula size plus 1 of Boolean functions. So these exponents that we get here, so this is defined for all values of p, and in particular we get something which is non-trivial for all p less than 1, since these functions both equal 1 when p is 1. And first, so if the original function f has decision list size m, this shows in particular for p being just a constant, we get, we shrink to expected size, something like square root of m. So in the setting where p is small, so where p is like 1 over log m, then it was already known by the switching lemma that the expected decision list size is at most a constant. And in fact, even the expected decision tree size is at most a constant. But the switching lemma doesn't imply anything in the setting where p is a constant or p is close to 1. So this setting is known as, sometimes called mild random restrictions, and results in this setting are important and have applications in de-randomization and Boolean analysis and DNF sparsification. Okay, so to give some context for our result, it's useful to make a distinction between these size measures and the corresponding width depth measures. So both Hastad's switching lemma, well, you can frame it in terms of converting a small width decision list to a small depth decision tree. And in a paper a few years ago, I gave a version of this result which replaces decision list width with log of decision list size. And then, so our result in this paper can be seen as a similar, has a similar relationship to a recent result of Lovett, Wu, and Zhang, where they prove a shrinkage result for decision lists, but in terms of the decision list width. So you can see our result as being along similar lines, but replacing width with log of size. Okay, so this, as I mentioned, this result for decision trees is a very simple proof by induction, which you can read on the slide. And good, so the our result for decision lists is based on the index function associated with a decision list, and in particular looking at the entropy of this index function under uniform random point in the hypercube. So the index function is just the first index, which is for which the clause CI is satisfied. And right, so we can note that without loss of generality, the index function of L is surjective, because if it wasn't, you could just delete any clause that where I is not in the image of the index function, and you'd be computing the same function. And so the simple observation in Lovett, Wu, and Zhang, the way that they bound expected decision list size, is by just bounding the expected size of the image of the index function of the restricted decision list. So something which, right, so in the longer version of the talk, I give a very short proof of a result along similar lines as what we show, but something which is simpler, and the proof fits into one page, showing that the average sensitivity of a decision list L is bounded by twice the entropy of the index function. Okay, so which gives a bound of 2 log n. Okay, and this is the whole proof of that. Good. So just to summarize, right, our main result was this shrinkage bound for decision lists. So some questions this raises. First of all, it would be nice, yeah, if there's some interesting applications of this result. And this result also suggests that the right notion of a shrinkage exponent for these measures like decision trees and decision lists is the following question. So what's the best, the smallest constant C, such that the expected decision list size of any functions at most order of the decision list size to the C times P for all P. And so our results, we have both upper and lower bounds showing that the constant for decision lists is between 1 over natural log of 2 and 2 over natural log of 2. So it would be interesting to pin this down exactly. And then, right, so we sort of settle the shrinkage of depth 2 AC0 formulas. And for higher depths, we conjecture that the shrinkage of depth D formula size would look like the depth D formula size raised to the order of P to the 1 over D minus 1. Okay.
Thank you. Thank you, Ben. All right, so maybe we should have Raghuvansh set up, and in the meantime, we might have time for a quick question. Okay, so maybe we'll save the questions for the discussion later. I see. Sorry, there's someone raised their hand. So let's see if we can.
Hi, I had a quick query with respect to the projection. Is there some hypercube, as I was just going through the paper, on which you are trying to project this?
So I'm not sure I got the question, but
I was just thinking with respect to the shrinkage and the projection of it. So, is there some result that also caters to that?
right. So maybe I didn't hear the full question, but I heard the word projection, so related to that.
Yeah, with respect to the
you can look at the other.
shrinkage,
So Avishai's paper in the conference that was yesterday's talk might address this. But yeah,
okay.
Continue in the chat after.
Might be interesting to see if we can combine both. Yeah. Okay. So let's continue to the next talk about computation over the noisy broadcast channel with malicious parties, and Raghuvansh would present the talk.
Thanks, Avishai. This is actually a part of a series of work by my co-authors and myself on the broadcast channel. And the broadcast channel is useful because it models wireless communication. Wireless communication does not need to be motivated. I wouldn't be given this talk without a wireless connection, but it is unreliable in the sense that it can be noisy, and also because it is involving a large distributed system, sometimes parties fail randomly, or some parties may be malicious. And therefore, we want protocols that communicate, that are resilient to both the noise in the channel and malicious parties. Now, one of these two, the noise in the channel, has been well studied, and we have the noisy broadcast channel, which models this. We know matching upper and lower bounds in some settings, so it's fairly well understood. But in this paper, we introduced the first result, which shows how to do computation over the broadcast channel when both there is noise in the channel and some of the parties are malicious. So that's the punchline. Let me now start defining things. We will be talking about the N-player broadcast channel, and this was proposed by El Gamal in '87, and we will consider the bit exchange problem. So there are N parties, and each party has an input bit. So let's say party I has an input xi, and what they want to do is they want to communicate so that at the end of the communication, all the parties know all the bits. Now, how do they communicate this? Well, there's communication is in synchronous rounds. In each round, exactly one party, which is the speaker here, he will be broadcasting, and he can send the same message to all other parties. This message must be the same, and it cannot be a different message for each party. It needs to be the same message for all other parties. If the communication is noiseless, then this message is received exactly. If the communication is noisy, then there is stochastic noise. So with probability 1 minus epsilon for some small epsilon, the message is received directly, independently by each party. And with probability epsilon, it is corrupted. So you receive something, let's say, unreliable. Now, for the bit exchange task, where everybody has a bit and they want to know all the bits, for the noiseless case, it is easy to see that the protocol must take n rounds. Everybody will take 1 round to send their bit. And because it's noiseless, everybody will receive it and the task will be accomplished. But in the noisy case, the naive protocol that comes to mind has n log n rounds. If you repeat a bit log n times and the players decode by majority, then with a polynomially, except with a polynomially small probability, they will be correct, and you can union bound and say that the whole thing works with polynomially small probability. But you can do better. And this is a very classic and very cute protocol by Gallagher in '88, where he shows an exponential improvement. Instead of, I say an exponential because what you really care about is the communication per player, which is just this factor of log n. So it goes from n log n to n log n, and it shows that you can do this bit exchange problem using an exponentially small communication of n log n. And I would have loved to talk about this protocol had I more time, but I do not, so I'll only talk about our result. But it is known that this is tight. This is a very technically deep lower bound that was shown after 20 years. That Gallagher's protocol is essentially tight, and you cannot improve it by more than a constant factor. However, all of these results assume that there are no malicious parties. And in fact, Gallagher's protocol breaks down even if there is one malicious party in the system. And we ideally want to tolerate a large constant fraction. So when there are malicious parties, even when there's only one malicious party, the best protocol you know is to just trivially repeat the bit log n times. This is not affected by malicious parties because everybody just does their own thing. And then you just decode by majority, and then you take a union bound. In this paper, we show a quadratic improvement, again, quadratic in the communication per player. We show an n root log n protocol that solves bit exchange when there is noise in the channel and when up to half the parties in the channel may be malicious. Okay, this is the main result. It is a quadratic improvement over the previous protocol. It is worse than Gallagher, but Gallagher breaks down for even one malicious player. But let me now spend a little bit of time on saying what exactly does it mean to compute something in the presence of malicious player. Usually, when you say computation of the broadcast channel, you want all the parties to know all the input bits. But this is all the parties to output the input bits of all the other parties. But this is not possible, and this is not possible for two reasons. One, some parties are malicious, so they will never output the input bit of all the other parties. Even if they perform the protocol correctly, even if they behave like good parties, at the end, they may just decide to output something random, and then you're doomed. So you cannot expect the malicious parties to output something good, but you also cannot expect an honest party, which is a non-malicious party, to output the bit of a malicious party. And this is because the malicious party, suppose it has the input 0. What it can do is it can, throughout the protocol, it can behave as if it has the input 1. And of course, the other honest party who doesn't know this will all it sees is that there is some party who's pretending his input is 1, and it will, of course, output 1 for this party. So this, again, is an impossibility. So we go for the strongest thing that is possible. What we want is, at the end of the protocol, all the honest parties output the bit of all the other honest parties, except with a very small failure probability. Okay, this is the notion of computation that we use. Our protocol is also computationally efficient. It's actually near linear, in fact. I think it's n log n or something. And this is the computational time that is needed at each party. That is n log n. N is, of course, needed because you need to output n bits. But other than that, we are just a log n factor away. And even aside of this result for the bit exchange on the broadcast channel, what we want to really emphasize is this notion of property preserving interactive coding. Interactive coding is just a fancy term for making something resilient to noise. And what is usually the focus in interactive coding is to make a protocol or something resilient to noise with a low overhead. So for example, if you have a communication protocol, you want a noise resilient communication protocol that has only a small communication overhead. But you're willing to compromise on all other aspects. In this paper, what we are saying is that the noiseless thing was n rounds. The trivial noisy thing was n log n rounds, so it was a huge overhead, but it had other good properties. It was a simple protocol, it was efficient, it was resilient to malicious parties, and it had all these nice properties. What Gallagher does is he compromises on all of the other nice properties. He loses the resilience to malicious players. He's still efficient, so I won't say that, but he loses the resilience to malicious players, but he does bring down the communication from n log n to n log n. And what we are saying is that this is not really necessary. You can even improve on n log n, even if you are not compromising on the other properties. And this is what we call property preserving interactive coding, that you not only maintain that the task is performed correctly, you also maintain some nice properties of the original noiseless protocol that you had for the communication task. Okay, so let me now talk a little bit. I think I have 1 or 2 minutes. Let me talk a little bit about the protocol and how it works. So we want to be resilient to malicious players, and malicious players can behave in several ways, but let us first consider an easy way, then I'll consider the adversarial or the hardest way. The easy way is, suppose a malicious player has input 0, and he starts behaving like his input is 1. Suppose he were to repeat his bit log n times, and instead of saying 0 log n times, he's just, or k times, he's saying 1 k times. Turns out this is an easy attack, because if he throughout behaves like he has an input that is the complement of this true input, then he will just output the complement and you'll be done. You can output anything for the malicious party, so you can just output the complement and you're fine. The harder thing for malicious, for the protocol is when the malicious party tries to switch strategies. It is when the malicious party, instead of saying 1k times, it says 0k over 2 times and 1k over 2 times. And now what fails is you cannot do any rounding. You cannot say that I will decode by majority because what he's attacked was exactly your threshold. It doesn't matter where the threshold is. He can put the same threshold in his attack. But let's say it has up. And what he did here was he failed your rounding scheme. Now you will round to 0 and 1 with equal probability, and this will be bad for the protocol. And to get around this, we propose this new notion of error-correcting codes, which are locality sensitive. So I'll talk about this notion next. A standard error-correcting code takes a short message. So this is a small space, let's say 0 into the k, to a larger space, 0 into the n, such that the images of all of these points are far apart. This is the distance property of an error-correcting code. And it says that if you're identical, of course, you will go to 1 point. It's a deterministic function. And if you're not identical, then you're far apart. A locality sensitive error correcting code preserves locality. It takes original messages that are close together to code words that are close together in a larger space. But if your original messages are far apart, then your two encodings will also be far apart. I am hiding under the rug some issues with the definition that arise due to the triangular inequality, because these 2 points here are as far apart as these 2 points here. And in my picture, these 2 points are close together, but the 2 points in yellow and green are very far apart. This is an issue. You cannot have such a clean definition. Sorry?
Can you try to wrap up?
Oh, sure. Sorry. You cannot have such a clean definition, but this can be taken care of in a nice way. And this gives us our definition. Last sentence, 2 sentences. We construct our codes using a random linear combination and show that it gives us the right proof, but we don't make any claims about optimality. So one way to improve our protocol even further is to just get better codes or show that these do not exist. Yeah, let me stop with that. Thank you. Sorry for going over time.
Thank you. Okay, thanks for the great talk. I guess we are a bit short of time, so let's move on to the next talk by Farah about communication memento, memoryless communication complexity.
Thanks, Avishai. Hi, everyone. So this is a joint work with Srinivasan and Arunachalam. So yeah. So before I start talking about memoryless communication complexity, let me briefly say, like, a recap standard communication complexity. So it was introduced by Yao in 1979, and in this so here we have a game where we have 2 players, Alice and Bob. They get their own input x and y, and they want to compute this joint function f of x, y. And obviously they need to communicate, and so at each round they send 1 bit at a time. And the goal is to compute the function by exchanging as less bits as possible for all possible x and y. Now, note that here Alice and Bob have unlimited time and memory, in the sense that Alice and Bob, they can compute any function that they want locally, and they also remember all the messages that they have seen previously. So we ask this question, what happens if the players have no memory in between the rounds? So let me elaborate what I mean by that. So we want that at every round, Alice computes the next message solely based on only her input x and the message that she has received in this round. And similar for Bob. So Bob is going to compute the message to send based on only his input and the message that Bob receives in this round. And the second way we differ from standard communication complexity is via how we compute the cost. So a cost in this model for computing a function f is the size of the largest message communicated between this 2 player, Alice and Bob. So let me explain this pictorially with this example. So again, we have Alice and Bob, these 2 players, they have x and y. Now note that they are in this memoryless setting. So in the first round, Alice applies a function f of x. So she chooses this function f of x based on her input x. So this is a deterministic function. And since she's starting, she applies this function on all 0 input, and she produces the first message. And then she sends the first message and then forgets about it. Now, for Bob also chooses a function fy based on his input y, and this function maps the incoming message to the outgoing message. So he produces this outgoing message, sends it to Alice, and then forgets about it. So they keep on doing this, and at some point we need to stop somewhere. So we say that, okay, if ever any player receives a message which looks like something like this, where we have all 0 with a trailing b, the output b. So, and we want this b to be the function value f of x, y. Now, and we need this to be true for all possible x and y. So intuitively, what is happening is, in this setting, we want that, so it is basically the size of a rewritable message register that the players send back and forth in order to compute the function for all possible x and y. Now, I have a really nice story that goes really well with this setting, but maybe I'll keep it for the discussion session. Now let's see how this model fits with the other space-bounded communication complexity model that we have seen in recent years. So here I'll describe 3 models that we have seen recently. The first one is Gardenhose model. It was introduced by Burman et al. In 2013. In this model, Alice and Bob, they compute this function in really this nice playful way. They have few pipes and they have hoses. They make the connection based on their inputs, and then they run water, and based on on which side the water ends up, they decide on the function value. The second variant that we have seen is the space-bounded communication complexity that was introduced by Brody et al. In 2013. And here, the player still sends one bit at a time, but the restriction is that now they are bounded by only SN amount of memory. And obviously, the goal is to optimize on the space that they are allowed to have. The third variant is called overlay communication complexity. It was introduced by Papa Constantiniu et al. In 2014. And this setting looks pretty close to our setting that we consider. So here, the only difference is that here Alice could have unlimited memory, and Bob doesn't have any memory. So at each round, Alice sends a message, and Bob could just either output 0 or 1 or continue, and they need to compute the function in this way. So what we did is we came up with this relation. So here, let's decipher it a little bit. Here, NM stands for no memory. So this is the memoryless communication complexity that we consider. So it's the cost of computing any function in that model. GH stands for Gardenhose complexity, and this is the space-bounded complexity introduced by Brody et al. And this is the overlay complexity. So what we showed using this framework is that these three models are essentially the same. And furthermore, they are also upper bounded by the overlay complexity. So in that sense, this memoryless complexity gives us a framework of seeing how all the space-bounded complexity models are connected. But moreover, it also helped us finding better algorithms for the Gardenhose model. So for instance, we had these two problems. One is disjointness with the quadratic universe. And the other problem is indirect storage access problem. So this is like x of y of z. And for both of this problem, it was conjectured that the Gardenhose complexity has to be like omega n square. But for the first problem, using this connection, so since it's upper bounded by overlay complexity, so we can use an algorithm for this model to come up with an algorithm here, we could reduce it slightly. But on the other hand, using this connection, using this memoryless communication complexity, we could actually get a linear protocol for the indirect storage access problem. So all these things, and there is also some non-trivial thing that we could say about space-bounded communication complexity that couldn't be seen before just by solely studying this model. So for instance, we could probably say that memoryless communication complexity model is perhaps a cleaner framework for studying all the space-bounded communication complexity models. So now, can we come up with some characterization of this memoryless communication complexity model? We know that standard communication complexity, we do this rectangle partition. So what is happening here since the players do not have memory? And it turns out that memoryless communication complexity can be characterized in terms of bipartite branching program. Now, bipartite branching program differs from normal branching program in this way that, so here you are seeing one example of a branching program. The only difference is that nodes are labeled by, instead of variables x0, it could be labeled by a function which is either computing on x or computing on y. So it could be a function on x or function on y. So it has this distributed nature. So this bipartite branching program is actually characterizes this memoryless communication complexity setting. We could also show connection with formula size. So we showed that any formula size S consisting of arbitrary fan-in 2 can be turned into a memoryless protocol of size 1 plus epsilon log S for arbitrary epsilon. Now this says that it basically provides a new way of proving formula size lower bounds for arbitrary functions by analyzing the memoryless protocol for the function. So it has it has the same essence of the Cosmos-Witderson game, where so here we are basically in order to prove a formula size lower bound, we could instead just study this function in the memoryless setting. But one thing to note that here constant really matters, in the sense that if we prove a log n lower bound versus the 2 log n lower bound, this should be treated differently. So for instance, if we prove a log n lower bound, that would give us a n formula size lower bound. On the other hand, 2 log n would actually give us a n square lower bound. So constant really matters in this model. Okay, so finally, I would describe some open problems. So there could be several open problems because it's a new model. But the main open problem is to prove a lower bound of some explicit function in the memoryless model, which would be c times log n for some c which is strictly greater than 1. So we could prove c equal to 1 lower bound for explicit function, but c strictly greater than 1 would actually imply 3 things. It would actually imply 2 things. First of all, it would imply a superlinear lower bound for Gardner's model, which is open. It would also imply superlinear lower bound for the bipartite branching program, which is also not known. And proving something better than 2 plus epsilon because of this formula sized lower bound connection would actually give omega n to the 2 plus epsilon lower bound for the general formula size. And this is the best is from Nechiporuk from 1966. So yeah, and we think that for this c strictly greater than 1, one candidate could be this distributed 3-click function. Yeah, so I would stop with maybe spending like 10 seconds on this. That we also defined like quantum version of different variants of memoryless model, and we could prove like exponential separation between the classical and the quantum counterpart. So yeah, I'll stop here. You can look at this link for the full version. On also the full talk is there. Thank you so much.
Thank you for the great talk. Okay, so let's move on to the final talk by Ilan. Ilan, can you share a screen?
Yeah.
Okay.
Can you tell me if you see the slide?
Yeah, we can see the slides. Okay, so Ilan Komogodsky will tell us about differentially oblivious Turing machines.
So hi everyone. So yeah, I'll tell you about differentially oblivious Turing machines. I'm Ilan Komogodsky, and this is based on joint work with Elaine Shi. So the motivation for this work is the following well-known fact by today, that even if you encrypt your database and you send it to somebody else, think of the cloud for that matter, then it's insecure once you start making accesses to your database. Namely, just by looking at where you access your data, even not knowing what's written inside the database, a lot of sensitive information might leak. And this is a problem that was observed already in the late 80s and early 90s by Goldrake and Ostrovsky, that introduced the influential concept of oblivious RAM. And oblivious RAM is just this very nice and useful approach. It's just an algorithm that whose task is to obfuscate the access pattern of algorithms. And slightly more precisely, or a bit less precisely, what it does is that it takes the access patterns of an algorithm and it sort of encrypts them, something like analogous to what encryption does to messages. And slightly more mathematically, what it does is it makes the access pattern of algorithms look independent of the underlying data. And what do I mean by being independent of the data? So there are naturally many ways to define it. 3 very common ways just define computational independence, meaning that a computationally bound attacker will not know by looking at the access patterns anything about the underlying data. There's a statistical variant which allows the distinguisher to be computationally unbounded. And there's even a perfect version where the attacker is unbounded and the distinguisher or the attacker is unbounded, and it has no advantage whatsoever. So this is what the oblivious RAM is, and it usually works in the following way. All of the constructions follow the same pattern. They first permute the data in the memory in some way, and then upon every access to the data, they reshuffle it. So this is how ORAM works classically. And okay. So So the state of the art of ORAM is has pretty much solved or advanced since the introduction of this problem about 30 years ago. So by now we know essentially that any program, any RAM program that you give me, I can make it oblivious, or I can make it a different program or that implements the same functionality with just very small overhead in terms of the amount of accesses that you need to make. So for example, if you give me a RAM that works on n cells with n memory cells, then I can simulate every single access to the memory with something like log accesses to the memory. And assuming one-way functions, the construction will be computationally secure. If we want statistical security, then we need to make something like log squared accesses for every access. So this is pretty great. And it's also great because we have matching lower bounds. So we know that logarithmic overhead is necessary. So there's nothing we can do to improve on this. And something very surprising is that this logarithmic overhead is necessary even for very specific functionalities. So even if you consider very simple algorithmic tasks or data structures, we already know that for them, if we want to make them oblivious, we need logarithmic overhead in the amount of accesses that we make. So this is the state of the art for ORAM constructions. And a couple of years ago, Chen et al. Introduced a meaningful relaxation of obliviousness exactly in order to see if we can go below the logarithmic overhead. So they introduced a notion that they termed differential obliviousness, and the name comes from the concept of differential privacy. You'll see in a couple of slides when I define it why it's inspired by it. But then a year later, there was a very surprising result showing that even if you consider this significant relaxation, it's a very strong relaxation of security, it guarantees much less about privacy, then the cost of a general ORAM, or a general differentially oblivious RAM, is still logarithmic. This was a very surprising result, but for specific functionalities, we can actually do much better if we consider differential obliviousness than obliviousness. So for instance, we have tasks, we know tasks that the best construction that we have, which satisfies full obliviousness, requires logarithmic overhead, while if we settle for the weaker notion of differential obliviousness, then we can obtain it with doubly logarithmic overhead. So let me try to define what differential obliviousness is. So let's first talk about the setting or the model. So the setting consists of a CPU. It's this green box in the middle of the screen. The CPU can be randomized. It has a source of randomness. And the input for the CPU is a sequence of logical accesses. It could be any algorithm that you run or any data structure that you execute. You can just translate it to a sequence of inputs to your RAM. The CPU gets those accesses, those logical accesses, and translates them into physical accesses. And the attacker is viewing those. He tries to learn something about your input. So since we're talking about differential obliviousness, which is similar to differential privacy, we'll consider a neighboring input sequence, which is an identical sequence of operations, of logical operations, except that we're going to change one location. So just in this example, I changed the 3 from the end, the third from the end access to be something else. So these two inputs are neighboring. And what we want is that if we execute the left experiment or the right experiment, then they will be indistinguishable. And what do I mean by distinguishable? So it's the same definition as in differential privacy. What we want is that the probability that you see the left sequence of physical accesses is very close to the probability that you'll see the right sequence of accesses, the blue sequence of accesses, except that there's this e to the epsilon multiplicative factor and an additive delta factor. So this is the definition of differential obliviousness. And here's our result. It's just one slide. What we show is that essentially any Turing machine computation can be made differentially oblivious with doubly logarithmic overhead in running time. So let me parse out the result. So consider a Turing machine computation that runs in n steps. Any Turing machine, it has this tape and it has a head. The head can move left and right. And assume that your computation makes n steps. So n movements to some direction. Every movement is to some direction. There's a very famous result from the late 70s by Pippenger and Fisher, showing that any Turing machine can be made fully oblivious. So it can be made such that it's completely independent of the underlying input or program that you execute with logarithmic overhead. This is like a very famous and influential result from back in the 70s. We show that if you settle for the weaker notion of differential obliviousness, you can do it generically with only doubly logarithmic overhead. We also know that we also show that there is a lower bound, a matching lower bound for our upper bound. So doubly logarithmic overhead is necessary. Our lower bound is in a restricted model, which is called the Bolzen-Binz model, where the CPU, where the server cannot really look at the elements that you store, but it can only see them as opaque balls. So it's a weak model for a lower bound, but it's still a lower bound. And we actually know that there is a lower bound for full obliviousness. So there's no construction that improves on Pippenger and Fisher if we want full-fledged obliviousness. This follows from the work I mentioned earlier. And this holds for very simple tasks like a stack. So we just want to make a stack oblivious. It must cost logarithmic overhead, but if we want to make it differentially oblivious, we can do it with doubly logarithmic overhead. And a lot of technical effort in this work is devoted to preserving the various properties of the Turing machine that is given to us, so we can handle multi-tape Turing machines, and we want to preserve that number, and we want to preserve the alphabet size and lots of other things related to Turing machines. And one implication of this result is that differential obliviousness is strictly weaker than obliviousness. Until this separation, there was no separation between. There was no evidence that differential obliviousness is easier to achieve than full obliviousness, even though it looks significantly weaker. So this is our result. We use two tools. I won't have a lot of time to tell you how the construction works, but just in one sentence, the tools that we use an oblivious Turing machine. You can think about the one of Pippenger and Fisher, for that matter, even though we need to tweak it a little bit. And the second tool that we develop is a Turing machine that estimates the location of the head of another Turing machine while maintaining differential privacy of that estimate. That's the main technical thing that we develop. And this is where I'm gonna finish. Thank you.
Thank you. And I want to salute Elon for giving the talk at 2:30 a.m. in Israel time. So yes, that's pretty impressive. Okay, so let's open the floor for questions to all speakers. I know that I have a bunch of questions, but feel free to unmute yourself or raise your hand, or you can also ask questions in the Q&A if you want.
Hi. Ian, I had a query with respect to the memory footprint. So what's the optimal memory footprint for this algorithm, which for the overhead that you achieved?
It's constant. Yeah, the blow-up in memory is constant.
Okay. So the scalability, if I look at it from a distribution perspective, those scalability issues won't be a factor for the,
what are we scaling?
Okay. With respect to the algorithm,
you mean the constants?
The data, the data.
You mean the constants?
Yeah, the inputs. The input size.
I'm not really following. There's only one parameter. There's only the number of steps the Turing machine does. could be depending on the input, it could not depend on the input. But there's only one parameter.
Yeah, I agree. There's only one parameter, but from the practical perspective, saving those stack in the memory. So I was thinking more in terms of the
so we have only constant
results.
overhead. Yeah. So we have only constant overhead in the memory size. So it shouldn't cost you too much, and the constants are pretty small. Okay, I didn't implement it, but they seem like smaller than 10, maybe.
So, do you have some empirical results associated with this?
No, I didn't implement it, unfortunately.
Okay, thank you.
Okay, thanks. Ilan, I wonder. So this notion of near neighboring sequences we refer to the head movements, right? Did I get it?
Yes.
What about the notion of like neighboring inputs? Did you consider that as well?
So it's really hard to define because neighboring inputs might translate to extremely different movements, right?
Mm-hmm.
So, and it doesn't really make sense to maintain privacy once you, like your two instances, one is go left and the other is go right a bazillion steps. Like I can't really hide which input you're using, right?
Okay.
So yeah, it's really impossible to do anything. There's one thing that I didn't say because I didn't have time, is that when I talk about neighboring inputs, I only talked about one location that differs. But you can actually generalize it using, group theorems, differential privacy group theorems generically. So you lose something in the bounds, but it generalizes very nicely.
I mean, how many modification can you get before you hit the log? The n log n. You can always do it with n log n, no matter how many changes you have. So which?
No, so you lose in privacy. You don't lose in complexity.
Okay. I see.
So I need to think about the dependence on epsilon and delta. I need to calculate.
Okay.
Because there is dependence on epsilon and delta, and epsilon is a constant, delta is a negligible function. So I need to think. I need to just look at the equation. It's not hard to work out.
Can I ask a quick question of a previous speaker? For Raghuvansh, I wanted to ask you about the concept of property preserving interactive coding. I just wanted to ask, do you mean it preserves the specific properties you mentioned, such as resilience to malicious adversary, or do you have some general definition of somehow preserving all properties, or is it a formal notion that you're talking about?
No, it's not formal. It's just we take a noiseless protocol. We see that the noiseless protocol has low communication, plus it may have some properties that we want to preserve. And the goal is to design a protocol that is resilient to noise while preserving the properties we wanted. It's not that any protocol for the original thing will be preserved. For example, one property is that it has communication N, and you obviously
sure.
This. So we select some properties, and it's more an ad hoc transformation that preserves what we wanted to.
Got it. And can I also ask Ilan a very quick question about just the definition, not for Turing machines, but the general definition of differential obliviousness? Yeah. Let's say it was RAM, where you have two sequences. Does it matter for the definition if the sequence is adaptive or not adaptive, or does it not really matter?
So for the definition,
I mean, because if you say, if you change the third from the last, but somehow it might depend on the answer, what will happen next?
No, it should not matter. I think the lower bound does not do that. Like we have a lower bound, right? That's the only result we have that's meaningful. And that one doesn't even use the property that you just mentioned. The sequence is completely fixed there, except like one thing. And if Avishai is still here, the answer is that, yeah, I can tolerate a group of size log. So it means that only things that are like log apart and not just distance one. Okay. Avishai is still here.
Yeah, I'm here. Thanks.
Because it degrades exponentially with epsilon. So.
Okay, great. I really enjoyed all the talks. I have a question for Shivam. So first, I mean, you mentioned that the analog with Talleyrand's result, and you mentioned that it was tight, but I didn't get whether your result is tight, whether you know that it cannot.
Right.
Prove.
So we don't think it's tight. In particular, we think Talleyrand. Actually, can I put my slides back up?
Sure.
Yeah. So we believe that something similar over here should hold, but with Talleyrand's C function, not our phi function.
Mm-hmm.
So like we still have this additional logarithmic factor, and Talleyrand's result is tight for two Hamming balls of like correctly chosen volumes, and our result for like the conjectured optimal result with just a log factor over here as opposed to log squared, we have two sets which match that conjectured band. So yeah, we like logarithmic within logarithmic factor of the optimal.
Okay, thanks. And another question. I mean, you sort of showed these results one next to the other. Is there any formal connection between these results?
What do you mean?
I mean, between the correlation of monotone Boolean functions and so symmetric convex bodies under the Gaussian measure.
I'm not sure if I'm following your question. Are you asking if there's like a way to go from like a monotone Boolean function to a symmetric convex set of a
Yes.
space?
Yeah. Is there a formal connection between these questions, or is it just an inspiration?
Yeah, it's sort of an analogy. There's no formal connection. But like some things seem to hold, like, dictators over the Boolean hypercube seem to correspond to slabs. Slabs such as, sorry, my slides on, it's weird, it's frozen. Or things like, majority seems to correspond to the sphere.
Mm-hmm.
So there seem to be many analogies, but there's no formal connection.
Okay.
Yeah.
And maybe another question is, are there any application of this new quantitative correlation inequality?
I don't know of any real applications. To be completely honest, I'm not sure what applications of Talleyrand's result exist. I mean, there's many theoretical implications, right? Like Talleyrand's techniques, like his main lemma is used to prove many things in Boolean function analysis, like the BKS theorem.
Mm-hmm.
So again, like I'm not sure if there's a direct application of these quantitative correlation inequalities. I might be wrong.
Thank you.
Yeah.
Again, anybody feel free to ask question to any of the speakers.
I guess I have a stupid question. So I also worked on interactive coding a little bit, but I've always wondered, like, has anyone tried to like implement or deploy interactive coding protocols? Like, this is for the last but second speaker.
Sorry, can you please repeat your question?
I was just saying, like, I've always wondered if anyone has tried to like actually implement or deploy interactive coding, any type of interactive coding protocols. Like, has this line of work and being considered like for any type of implementation or usage? Like, yeah.
Is this question referred to Raghuvansh, maybe?
Yeah, sure. Sorry, maybe it was not last time. I'm so stupid.
Sorry.
No, we had 6 people, so that's fine.
I felt this was for me, but I was not sure. So one application I know of is the application to resilience circuits. It's not like an actual deployment of anything, but it is an application of the theory to another aspect of theory. The problem there is, suppose you have a formula, or let's say a formula, not a circuit, and you know that some of the gates in the formula can have errors, but you still want the formula to compute the same function. Then what you can do is there's this Tausch-Merwittersen transformation that takes a formula to a circuit, to a communication protocol. You can run interactive coding on the communication protocol, and then you can transform it back to a noise resilient formula. So that is one connection I know. I do not know of any actually engineering applications of this area.
Okay, thanks.
If we are asking questions about your talk, I have a bunch of questions. So, so just a clarification questions regarding the malicious parties. I guess I didn't really understand maybe the framework. Like in particular, is it clear in every round who is speaking, and can the malicious party interfere? And if so, that seems a little bit.
So that's actually a great question, because like when we wrote the paper, I would have given one answer to this question, but now I can give another answer to this question. So let's see. In general, in our protocol, we do not assume anything from a malicious party. We just assume that it can do whatever it wants. But therefore, when we're defining the model in the paper, we assume that for every round, you know who is speaking in that round. And this is because if you do not know this and you allow the parties the freedom to speak whenever they want, then the malicious parties can just keep talking in every round, and they will not allow any, they will just like choke the channel, will not allow any communication to take place. So this model and our protocol is non-adaptive. Non-adaptive is exactly what I said. For every round, you know who is speaking in that round. And our result is for the non-adaptive thing. There is the adaptive broadcast channel. And in the paper, I'm not sure we said this, but at least we were thinking, okay, this definition is clearly breaking down, and you cannot have malicious and adaptivity at the same time. But now we have a model that does this. And the model turns out to be that you do not assume that the parties are malicious. Instead, you assume that they fail. I think this is the right generalization. When you have an adaptive channel, then the parties will just not be talking. They will not talk even when they're supposed to. And it is not clear, like at least all the protocols we know of will not carry over even if the parties fail. And it is an interesting problem to define such a protocol.
Okay, thank you. Very interesting. And what about like if you allow them to interfere, but in a bounded way? Like, you know, in error correcting code, we usually assume adversarial noise, but under some budget, like you can corrupt at most epsilon fraction of the.
Okay, so that's another great question. Oh my God, so many great questions. So when you have a distributed system, then actually you should really read the paper because we cover all of these questions. But anyway, when you have a distributed system, then it turns out that adversarial noise tends to be, I don't know what's the word, but like notorious, because what you can do is if you have n parties, and even if you have a 1/n fraction of adversarial noise, you can just focus it on one of the n parties. And then because that party is not speaking, then you cannot just compute the identity or the bit exchange problem. And usually it's not that it wasn't studied, it was studied in distributed settings, but usually the results go like, okay, you clearly fail when you have 1/n adversarial noise. But what the result says is that as long as you have less than 1/n, let's say you have 1/10 in adversarial noise, then the protocol will work correctly. In the paper, we take inspiration from a definition from malicious players to give a new definition of correctness for adversarial noise. And the definition goes like this. You have some, let's say even a constant fraction of adversarial noise. So the adversary can kill a constant fraction of the players. Let's say it's 0.01 for concreteness, so 1% of adversarial noise. But what we want is, instead of being correct for all the players, we allow the protocol to fail on a constant fraction of the players as well. And again, this is another like conceptual contribution of this paper that gives you a definition for adversarial noise that does not have the 1/n bottleneck, and basically can regard the parties that were choked by the adversary, that were bullied by the adversary, as being malicious. And now you want the protocol that is correct on the remaining parties. You can even give some slack. You can even say that if the adversarial fraction is 1%, I'm allowing you to kill 5% of the parties. Just give me something that's correct on 95%. So there is also that, there's room there. These are all great questions, and this is all like future work. Yeah.
Thanks.
Maybe future work, maybe there is no work.
Okay. Okay, I have some questions for Ben. Ben, are you still around?
Yeah.
Hi. So you mentioned some possible motivation coming from, mild random restrictions were used in pseudorandom generators by the famous work of GMRDV. Do you see any potential de-randomization of this result? I know that recently, Sander Kelly de-randomized one of your results, and so.
Yeah, I'm not sure. So the short answer is I haven't thought about it exactly, but yeah. So I mean, a lot of the results use, look at width as opposed to size. So I'm not sure what the I'm not sure what the potential applications might be in this case.
Hmm. And do you think that there's that the results don't say something on they say something only on size and not on width? Trying to understand your comment.
So the width version of this result is in this paper of Lovett, Wu, and Zhang that I mentioned. Mm-hmm. But yeah, no, really, I'm not sure. I'd have to look. I haven't thought much about the potential applications in de-randomization. I tried thinking if this might have applications to things like Mansour's conjecture or sparsification, not so much about the de-randomization.
Yeah, great open questions. One thing that comes to mind is, random restriction naturally composes, right? If I do a P random restriction, then a Q random restriction, it's just a P times Q random restriction. And then it seems natural that the bounds that you would get would also compose nicely. So based on that, does it give rise to a natural conjecture of the right behavior?
So right, good. So that shows that the bound you get should be convex. So this exponent, this log base, whatever of it, this exponent is convex, and if it wasn't, you could make it so by taking compositions. But
I see. All right.
Just a quick follow-up. So the projections that you had taken, I was just wondering which algorithm did you take into account? I might have missed that.
See, still not sure I understand the question.
So maybe just to clarify, so Ben's result is with respect to random restrictions, where you pick each coordinate, you keep it alive with some probability, let's say P, and with probability 1 minus P, you flip a random bit and you set it to this constant.
But those projections have to be taken into account since you need to weakly assume those probabilities into a particular objective. So I was just thinking those weakly, or I might be missing it. I don't know. Correct me if I'm wrong. Yeah, please.
Yeah, I'm still not sure exactly what's being asked. So in the paper of Avishai or in Yuval, they introduce this a generalization of random restrictions. In fact, they can be projections. It's actually interesting if those could be made to work in this argument.
Oh, okay. Okay, cool. Thanks.
All right. Any more questions to any of the speakers? I guess we are a little bit late already, but
I had a question for Sasha, actually, if he's still around.
Sure.
Yeah. So if I understand the result correctly, you say, one would like to prove circuit lower bounds by saying, look, if circuits of a certain depth can be reduced to constant depth with a certain size. And so you say, well, here's something that works on any depth, and it just depends on the size.
Right.
But the size that you get at the constant depth is very large, hopefully not too large that you can't prove anything. And so you're looking for lower bounds. To turn it into an actual lower bound, you'd need a lower bound on that constant depth.
Right.
What techniques do you think, do you have a particular technique in mind that you think could be extended to those kinds of constant depth but very large size circuits to prove lower bounds for this? Or how do you think this would be turned into a lower bound for a natural problem or any problem?
Yeah. So no, that's an amazing question, and luckily we have tens of results that are proven very strong lower bounds for, say, depth-3 circuits, like really strong, just a little weaker than what we need for Wayland's result or our result to give any circuit lower bound. So in fact, we have tons of techniques. Just somehow magically, currently they don't give result that we need. But no, I don't think there is a lack of techniques. So essentially, we have a bunch of techniques for proving depth-3 circuit lower bounds. We have a bunch of different techniques for proving dispersor lower bounds, and they would also lead to the needed depth-3 lower bound techniques. Same things with rigidity or correlation with polynomials. I think these techniques are quite different, but they all would lead to depth-3 circuit lower bounds. So yeah, we have quite a few.
Okay, thank you.
Yep.
I had a quick query with Podder. So if he's on the call.
Yeah.
Yeah, I was thinking, why did you use bipartite branching programs here as the communication, the characteristic of your communication model? Couldn't you have modeled it in some other data structure? And if so, what were your other considerations?
Right. I think bipartite branching program came pretty naturally because this is how the model looks. Because if you look at like these two players, they're sending messages back and forth. And if you look at like any run of this game for particular X and Y, you'll see that any player cannot send the same message twice, because otherwise they don't have memory, they'll run into infinite loop. So it has this acyclic nature, and it also this bipartite in the sense that because like some messages are coming from Alice and some messages are coming from Bob. So when you try to plug this thing as a graph, it naturally gives you a bipartite branching program, because you start with this, like Alice always start with this particular node. You can think of like they always start with a particular node, and then it just walking along this acyclic graph. So yeah, it's like natural generalization that happens from this game.
Awesome, thanks.
I have another question regarding the model. So in the model, you only focused on the memory, complexity, and not on the number of rounds. What happens if we take into account both of them? And do we know that the model changes dramatically?
Yeah, so there are like it's possible to prove like time-space trade-off theorem. Like for instance, you could say like if you restrict round to be like let's say constant or something, then it can be, you can show that then we can prove like superlinear, like super logarithmic lower bound. And there could be like hierarchy theorems based on like what can we achieve using, let's say, k round versus k plus 1 round. Yeah, we didn't do that, but yeah, that's a possibility actually.
Okay, great, thanks. And maybe another question. So you mentioned this connection to formula, and you said that by what you can prove now, you can prove like a linear lower bound formulas, but we know quadratic lower bounds on formulas. So did you consider just the function introduced by Nadimpalli?
Yeah, so no, linear in the sense that, like, if we have, let's say, in memoryless communication complexity, if we prove like C log n lower bound, then that would translate as n to the C lower bound. So in order to get anything meaningful, we need to prove at least 2 plus epsilon lower bound. Then, because it's a translation from like general formula. So yeah, for formula, it has to be at least like 2 plus epsilon times log n lower bound.
Right. No, so I got that. So, but my question is, what happens, like, if you look at the problem that Nichiporuk proved the n squared lower bound for in your model, does it even make sense to consider this question in your model?
Right. I think like Nichiporuk proved one of the thing was like this indirect storage access. So we get like a linear lower bound actually if you try to go via this direction, because here there is a very simple log n size protocol.
I see.
Yeah.
So it's so the connection to formula is sort of one way. It's not.
That's right. Yeah, it's one way. It's not two way. Sorry, my light turned off.
Okay, great. Thanks everybody for the great talks. And I guess it's getting late, so I won't keep you away from getting some rest. So see you, and thank you very much.